Welcome back. Ready, set, go. I mean now go. Good job. You used US equals 1/2 kx squared. You also know UG equals mgh and k equals 1/2 m squared. And all three of them, US plus UG plus k, is mechanical energy. Now is the big lesson. We're going to put them all together and the unit will make sense. We'll learn why we did all this weird math for no reason, when we could have just used kinematics to find the answer to all the previous problems. This is a really cool demo. It would have been really fun in person, but we're not in person. Sorry.
Here we go. Good. I'll go again.
One more time, just for clarity.
Good. I'll go again.
Wow, what a great video. Okay, we're going to assume this pendulum had a stiff string that never stretched, so no US, only UG and K. A great drawing for a great lesson. The teacher pulled the ball all the way up to the student's head, and it was at rest, and she let it go. It was at rest, so K was 0, UG was not 0. Then she released it, and it gained K. It also decreased in height, so it lost U. So the ball has K, no, has U, no K. Sometimes people like to draw this little chart. I don't really care about this chart, but I'll show it to you. UG, K. The ball had lots of UG, no K. Down here, the ball had, we consider this height to be 0. It had no UG, lots of K. This y-axis is energy, kinetic or potential or whatever, energy in joules. And finally, it went up to the height at the end. In theory, about the same height, UG, K, high, low, 0. As UG decreases, K increases. As K decreases, UG increases. I wonder if they're related. If they're related, how would you describe the relationship? You probably have already heard, you probably already know, energy is conserved. For today, for us, mechanical energy is conserved. The total US plus UG plus K is some value. If none is lost, the initial value will be the final value. The ball will start with UG, and then it'll have K, then UG, then K, then UG. It'll never hit the kid in the face because it won't have more UG than it started with. It'll only have its same starting amount, so it'll only go up to the same starting height, H, not any higher than where it started. Of course, the kid might stand up and walk forward and get stacked, but that's not really related to this lesson. So mechanical energy is conserved. It doesn't get created or destroyed. The UG became 0, but it didn't disappear. It became K. Wow. Physics. So you can write delta E total equals 0. Total mechanical energy changed is 0. If you want to be crazy, you could write US plus UG plus K equals US naught plus UG naught plus K naught. They mean the same thing. Don't just memorize equations, understand what they mean, as per usual. Okay, what do you get if they're not conserved? There are definitely times when work is done and an object can start with energy and then it can be lost. Like, I don't know, like a rock can slide down a hill, but if it's a rough hill, UK might not be conserved. You guys think, what happens if it's not conserved? Oh man, it's really cold. I'm going to sort of warm myself up a little bit. What happens when energy is not conserved? Something, right? No. For us, it's heat. There might be things like sound and light and vibration, chemical energy even, but the only energy we're going to talk about that's not mechanical is heat. And the symbol is Q. If you guys took chemistry and you learned MC delta T, MCAT, same Q. Q is heat. So this is for when it's conserved. When it's not conserved, equals Q. If I have like a Tibetan singing bowl and it slides down a ramp, but all the potential energy doesn't become kinetic, some gets lost, that lost amount will be a certain number of joules of heat. If my Tibetan singing bowl has 100 joules of energy, of potential energy, UG, and it slides down a keyboard, it'll lose U, G, and gain K. So it started with 100 joules of UG. If at the end it has 100 joules of K, it was conserved. If at the end it only has 80 joules of K, 20 joules became heat, Q, and probably due to friction, warming it up. You can find it, because we won't use this chemistry formula because chemistry is pointless. We're using Q equals the work done by friction. I was just kidding. Chemistry is great. Don't tell anyone, isn't it? Okay, so that's conservation of energy. It's a simple idea, but putting it in practice is a little tricky. So I think we need to see some practical examples later. For now, why is it so useful? Why is it so important? Why did I spend a whole unit doing weird math to get to this? The common example is a pendulum. Another common example is a roller coaster. All that means is an object moving across like hills and ramps and stuff with, really important, zero friction. Ignore friction. Otherwise, if you have friction and displacement, you're going to have heat. Let's say there's some point in the middle, not the highest point, not the lowest point, somewhere in the middle, where the ball has UG and K. Maybe like half and half, something like that. Sure. Let's draw our favorite thing, the old free body diagram. So a pendulum is an example of a time when energy is conserved. In a pendulum, is work done? What do you think? Is work done as a pendulum swings back and forth? It is. It is done. Work is done. How can that be? We said work is a change in energy. That doesn't mean it's lost. It changes from U to K. So U becomes K due to work, probably by gravity. This is a really important idea that I should have mentioned in the beginning of the video, but don't really feel like editing. So, the important energies we talked about are potential in springs and potential in gravity and K. If you push a rock in space, it'll get K. That's the only kind you have in space. There's only two other kinds you care about, US and UG. When you do work, squishing a spring, the spring has potential, because if you let go, the spring will do work. When I do work against gravity, gravity has potential, because if I let go, gravity will do work. So those are the potential energies. So whenever we look at these problems, we're assuming friction doesn't exist. Friction doesn't do work. But gravity can do work, and a spring can do work. So this problem, what if I said, find the speed of the ball when it's at height, if this is h, what's the speed of the ball at h over 2, when it's half the height? If we try to do this with kinematics, it would be impossible. We could draw the free body diagram at a certain angle theta. We could say that's theta, then this would be theta. So yeah, you could do sine and cosine and find the acceleration and then plug it into some kinematics like v squared equals v naught squared plus 2ad. It would be two-dimensional. It would be pretty hard to solve. But I think could you do it? Is it possible? Tell me right now. What do you think, Sage? Is it possible? Yes. Can you do it? No. Yeah, well, Sage couldn't do it. And that's because it's actually impossible. As the pendulum swings, theta changes. So even if you found the acceleration at this point, that's not the acceleration over here or any other place. Every theta is a different acceleration. So you couldn't use it in a formula like v squared equals v naught squared plus 2ad, because a is always changing, because theta is always changing. And confusingly, ft is also always changing. So you can't solve this problem with kinematics. It's not possible. But there is a real nice way to do it with energy, with conservation of energy. Work is change energy. Gravity can do work. We can find the work done by gravity from mg and delta h. That's fine. Gravity does work to change ug into k. What about tension? Does tension do work? Hint, if it did, we could not do this, because there's no formula for the work done by tension, or formula for the tension force. In fact, as I said, it's always changing. So, why doesn't tension do work? If you guys remember, the formula was not work is FD. It was FD cosine theta. That's the thing. No matter what, whatever position the ball is in, the force of tension is always straight toward here. but the velocity, and therefore the displacement, is always along this arc. No matter what position you're at, F and D are perpendicular. Cosine theta is cosine 90 is 0. So Ft never does work. This makes it very nice. You don't need to know the force of tension and the direction of the force of tension at every single point in the problem, because it never matters. If you analyze this problem based on work and conservation of energy, you can ignore tension completely. And also time too, so it's like double easy. It should be no problem. We should get these problems as if they're like just baby problems, just like no problem at all. Just so easy, just the easiest physics. The same is true for roller coasters. All the roller coasters we'll look at are frictionless. It doesn't matter how crazy the crazy path is for the roller coaster. The only forces we care about are Fg and Fn. We'll say there's no friction in this roller coaster. Gravity will do work. Gravity will change this energy into this energy. Or if you're rolling up the hill, you're slowing down. So gravity is changing K into Ug because it's doing negative work. I should have asked that, but I forgot. So gravity can do work, positive or negative, as the roller coaster rolls. Will normal force ever do work? No. Same reason. By definition, normal force is always perpendicular to the surface, and if the roller coaster stays on the rails, it'll always be perpendicular to the displacement. This isn't always true. These aren't always true. Obviously, if you're like lifting a heavy refrigerator with a rope, tension is doing work. If you bounce a ball off the ground, normal force does work. In pendulums, tension never does work. In roller coasters, normal force never does work. So you have to analyze the problem and think, is energy conserved in this problem? Which is a little tricky, but big hint in the energy unit, most of the time it's conserved. Definitely in pendulum and roller coaster problems, it's conserved. So you can just say, oh, set the total initially equal to the total at the end, because normal force never does work, and that's very good. And friction never does work, and therefore the energy lost is 0. Springs aren't that interesting, but it's the same idea. Whenever you see a spring in physics, you usually assume, you're usually told that the floor is frictionless, there's no friction or air resistance. There is work done. If I stretch the spring, I'll have, I forgot what springs look like. If I stretch the spring, I'll have lots of US, no K. If I let the spring go, the mass will shoot backwards. I'll have no US, lots of K. Or it could be in the middle, and I could have some of both. But no matter where the spring is, 1/2 mv squared plus 1/2 k x squared should be constant if there's no work being done on the mass and spring system. If there is work done by friction, they would not be equal. You would be missing some factor Q, where Q because the work done by friction is FFD usually. If you have solved this, FF is probably constant, so it's not that bad. Okay. So I can't really show that much else. The idea is simple. The tricky part is just reading the problem and identifying what energy exists here, what energy exists here, what energy exists here. Then you just add them all up and set them equal. Obviously, if you miss one in a conservation problem, you're not going to get the right answer. You need to have every single energy accounted for in every step, and then set all the energy in step 1 equals to all energy in step 2, and solve for whatever is asked for. Usually they'll ask you like, what's the speed after the roller coaster has fallen this far? Or what's the height that the pendulum will reach? Or how far will the string be stretched? Will the spring be stretched when the mass is moving speed v? Don't worry, I got lots of practice problems for you, and they're going to be great. Such as this one, the loop-de-loop. Lots of roller coasters have loops. And in roller coasters, obviously, there is friction, and also, obviously, the car is attached to the rail so it can't fall off. But what if it wasn't? If the roller coaster needs to go through the loop of radius r without falling off, what height h does it need to start at from rest? It's a tricky problem. The trick that people get tricked by is they say, oh, it's conserved, so same height. So they'll say, oh, you gotta start at some height, the highest place you can reach is the same height. So h equals 2r. Do you think that's true? Is h equal to 2r? Nope, it's not. Look at this problem, Daisy. I see it, Mr. Lamb. What's the starting speed of the roller coaster? 0. V naught equals 0. It starts at rest. Good. What's K naught, the initial kinetic energy? 0? Yeah, obviously. If V naught equals 0, K equals 0. Great. When the roller coaster is upside down, what's the velocity v? 0? No. What's the velocity v? It has to have centripetal force. Fc equals mv squared over r. Yes. Good job. Don't throw your v's. It's okay. Daisy. You redeem yourself. What's the centripetal force at the top? Gravity, yes. At the top, if the car just barely makes it over, there's still a downward force, centripetal force. It's gravity. If the car is not attached to the rails and just barely makes it through the circle, at the top, Fc equals Fg. We already did this in the circular motion unit. So you'll get h equals 2r if you think that the roller coaster comes to rest at the top. But if you think for a second, that's not really ideal. If the roller coaster just stops at the top of the loop, then it's not going to go through the loop, and also it'll fall. And also, that's not really a good ride if it doesn't make it all the way to the end. So at the highest point, k is not 0, because v is root gr. At the highest point, k is 1/2 mv squared equals 1/2 mgr. Good job, Mr. Lamb. Thanks. What's U at the highest point? Sage? Well, I don't want to get thrown against the wall. MGH and H at the top of the circle is 2R. Yeah, that's right. So at the top, the only energy is UG. At the top, UG equals MGH. Over here at the top of the loop, we'll call top, sorry. At position 1, U equals MGH. At position 2, U equals 2 mgr. K is not 0, it's 1/2 mgr. So E2, which would be U2 or UG2 plus K2, 2.5 mgr. Set this equal to this because it's conserved. Energy is not lost. The total here at position 1 equals the total here at position 2. If I'm going too fast, ask me to go over it in class, please. As is very, very common, N cancels, G cancels, H equals 2.5 R. So H equals 2R was pretty close, but you need a little more height, 2.5 R, because at the top of the loop, the car is still moving. Are you guys tired? Is that long enough? Are we done?